So, our presentation will outline an introduction, a rationale, mission objectives, data products, target applications, assumptions and technical requirements, mission architecture, programmatic elements, and a final mission performance estimate. So, macroplastics. Plastics can be derived from a number of sources, including cellulose, coal, natural gas, salt, crude oil, and crude oil. A macroplastic is any plastic that is greater than 5 millimeters in diameter. So if we look at some rationale, in 2015 only 9% of plastics were recycled, and a huge 79% of plastics accumulated in landfill or natural environments. In the next 10 years, these figures are expected to amplify, and this will be further driven by the resultant increase in PPE use as a result of the current COVID-19 pandemic. Now, various questions still remain unanswered, and this is why we believe that PlasticSat could become a very useful ally in the Earth observation team. We have little knowledge of the amount of time macroplastics remain at the surface of water. This could be dependent on location and polymer type. We are intrigued to answer the questions over the source of these macroplastics, as well as obtain values for actual mass of plastic covering oceans, as currently there are only estimates available. Macroplastics display a range of vertical patterns when travelling in oceans. These are often driven by numerous factors including plastic density, photooxidation, storms, vertical mixing, and biofouling. Now onto the data products. The PlasticSat will measure the location and quantity of macroplastics in oceans using near-infrared to detect them. Passive optical sensors will detect the location of the macroplastics across the oceans and relay them into maps to be used either alone or in conjunction with other information. The concept hinges on determining the main sources of these macroplastics by identifying them before biofouling or significant breakup of the plastic occurs. This is a viable concept, as proven by Bierman and others in 2020, although in their study they used Sentinel-2 data, which had a spatial resolution of only 10 meters. We therefore plan to have a significantly higher spectral and spatial resolution to increase the accuracy of our data products, and also allow for detection of smaller macroplastics that are not necessarily grouped together in the oceans. As different types of plastics such as polyethylene and polystyrene have different spectral signatures, it is possible to distinguish each type dependent on their reflectance they present in the near-infrared sensor. This is a method commonly used in the recycling industry to separate different plastics. Whilst looking at the near-infrared reflectance of the ocean, the sensors would capture other variables such as sea foam, seaweed, wood, and other debris. Each of these have a specific spectral signature on the near-infrared spectrum, meaning that they can be differentiated from other plastics. We're looking to use the Bayesian algorithm to train the computer learning to recognize different types of materials, as we will only need a very small sample size, and it has already been proven to work with satellite plastic detection. Moving on to mission assumptions and requirements. We proposed 2 satellites for this mission, as the other requirements would struggle to be fully achieved with only 1 satellite. We also proposed 3 spectral bands, one at 700 nanometers, one at 840 nanometers, and one at 1100 nanometers. The 840 nanometer generates peak plastic reflectance, whilst the 700 nanometer will be used to create an NDVI, a normalized difference vegetation index, to eliminate any organic material. And finally, the 1100 nanometer band will be used as it is also highly reflectant for plastics and also highly absorbent for water. This satellite will have a very high resolution of 3 meters to identify smaller and less clumped macroplastics. A sun-synchronous near-polar orbit will be used in order to compare measurements more accurately. An inclination of 98 degrees will be used based on knowledge of Rapid Eye and Sentinel-2. A return time of less than 15 days in order to catch plastics before submergence will also be utilised. This reduces the probability of cloud cover on the majority of images. We also expect at least a 7-year life expectancy of the satellite based on other satellite missions. The main ground segment will be the European Space Agency's one in Germany. However, other ground stations across the globe will be utilised as the satellite moves over the poles. Here's just a clear outline of the things I've just gone over, as well as some ground segment information here. Finally, this is part of synergy with other missions. There's obvious overlap with Sentinel-2 systems. There's similar bands, but the goal is with a higher resolution and a higher revisit time. This will produce much more accurate data on plastics that Sentinel-2 cannot achieve. And finally, mission performance. We can fairly accurately measure the effectiveness that this mission will achieve. We expect to produce user-friendly data which accurately defines the spatial extent of macroplastics covering global oceans. Numerous studies show that this would be possible, so there is very little to suggest that the program would not be feasible. All of the technology needed is currently available. Less investment would be needed, therefore, as it is already easy to get. Well-backed algorithms for plastic reflectance and atmospheric correction have already been derived as well. So overall, very little effort would need to go into achieving this satellite mission. However, the effects of it may be very useful in future. Thanks very much for listening.